Hello, my name is Nikhil, and today I'll be presenting Alohamora, an adaptive system that uses reinforcement learning to generate push and preload policies for faster page loads. This is joint work with Murali and my advisor Ravi from UCLA. We're all probably familiar with the page load process, but I'll start with a quick overview. When the user loads a page, the browser sends a request for that page to the server, and the server returns an HTML response. The browser then starts parsing the page and discovers that it needs other resources, such as a script, to continue. So it'll pause rendering the page and download, parse, and execute the script before getting back to the HTML. Down the line, it might discover some other resources, which also cause it to wait on the network. This process of fetching, executing, and discovering objects repeats recursively until the page is loaded. This can be modeled as parsing a dependency graph between a page's objects. And in this model, the big problem is that the browser must incur serial network fetches to resolve edges, especially on mobile networks. It's the critical path in these dependency graphs that cause slow page loads. To address the problem of serial dependency chains, HTTP2 introduced push, in which a server can attach extra resources in responses. This means the server can send back that script without the browser having to block to fetch it. It also supports preload, in which the server can hint to the browser to download resources from other origins, which helps the browser fetch third-party content right after parsing the HTTP headers and without having to execute the parent object. Together, we can define a push preload policy, which is the specification of which objects to push or preload from which parents, and this helps eliminate those blocking network fetches. These techniques have potential in alleviating network overheads, but need to be applied very carefully to maximize benefits and not hurt performance. The fundamental issue is when we apply a policy that causes resources of different priorities to contend with each other. Let's look at an example. A browser sends a request for the HTML page and receives a response. After a short while, the browser discovers a dynamically addressed JavaScript file that it needs to continue loading the page. During that time, the network is sitting idle, so the server can afford to push just enough to fill the gap before the browser needs the JavaScript. Any more, and the pushed resources would contend on the network with the higher priority JavaScript. On the other hand, a slower device might spend more time parsing and executing before it discovers the dynamic JavaScript, which means the server can afford to push more resources in that gap. This means that policy efficacy is critically dependent on the specific conditions of the page load. To evaluate how important catering to a specific environment is, we performed an experiment. Over many pages, we first measured the load time in a baseline environment. We brute forced push preload policies to find the best for that environment. Then we changed just one attribute of the environment, in this case 2.2 gigahertz to 1 gigahertz, and again found the best push policy for the new target environment. Finally, we compared the performance of these two policies on the target environment. With just a single edit to the environment, there's a pretty significant performance difference. The best policy for the target environment performs much better than the one from the baseline. In fact, the best policy from the baseline does slightly worse than the default load at the median. And these trends hold as we varied other environmental factors, such as network speeds and cache contents. In particular, policies that optimize for a different environment can forego up to 30% of the potential benefits and degrade performance by up to 20% compared to the default load. So push and preload have promise, but they have to be configured for a specific environment. As opposed to existing systems, which use static policies, we built Alohamora, an adaptive system that generates push preload policies on the fly, given some real-time observations about the page, client device, and network. To generate these policies, it applies reinforcement learning in an offline training phase. I'll first describe what reinforcement learning is, how we applied it in Alohamora, and what the practical challenges were to realizing this on actual page loads. At a high level, reinforcement learning tries to find the sequence of actions that produce the highest cumulative reward, given some observations from an environment and a reward for each chosen action. In our case, the environment is the browser in certain network conditions, running on a particular device. In that environment, we would like to evaluate push preload policies. And for each one, we'd like to measure its performance as the reward. To learn these policies, we use a neural network with several inputs describing the environment. The output is an action that either describes an object to push or preload. In each iteration, we end up with a policy based on the current parameters of the neural network. By training on many pages and environments, we can learn the parameters that produce the best policies. Although the application of RL is straightforward, there are multiple challenges involved in implementing this on real websites. First, websites commonly serve thousands of pages. Training on all of them would be impractical. To overcome this, we leverage the observation that groups of pages for a given site typically share significant structural properties. For example, the New York Times has articles, subsections, and blog posts, distinct types of pages, all generated from templates. Since these structural properties govern the performance of push preload policies, we can train a single model per cluster. Second, even for a single page, it's too slow to consider all the potential policies. The number of policies is exponential, and worse, testing each policy would require a full page load. As a result, training a page for a site like the New York Times would take over 10 days for a single environment. To overcome this, we introduce a novel page load simulator that can evaluate a policy in milliseconds instead of seconds. To solve the first challenge, we want to cluster pages and capture structural similarity such that pages in each cluster have push policies that all perform similarly well, while also not having too many or too few clusters. Our key observation is that policy efficacy is correlated with resource utilization, which is dependent on page structure. Representing each page as an annotated page dependency tree correctly captures how the browser will parse the page, which in turn dictates when network and compute resources will be used during the load. And generating these trees only takes one page load. Once we have this annotated tree for each page, we can use a tree edit distance algorithm to create a distance matrix containing distances between every pair of trees, and then cluster the pages. We find that this approach works pretty well. When an optimum policy for one page is transposed to another page in the same cluster, it achieves 82 to 100% of the benefits as the page-specific optimal policy. Whereas when policies are applied to pages in other clusters, they perform much more poorly. The ultimate takeaway is we can train groups of pages. We can group pages to train a single model per cluster without losing much in terms of push preload benefits, while drastically reducing server-side training costs. Now that we've narrowed down the pages to train on, the second challenge is that it would take too long to actually load pages to evaluate each policy during training. To solve this, we'd instead like to predict policy performance as accurately as possible while being much faster than the full page load. We want this to be faithful across arbitrary environments and realistically model cross-stack constraints. Our key insight here is to perform a one-time capture of an unshaped profiled load of the page, and then model the browser as a multi-queue system that modulates delays accordingly. When we capture a default load, we learn the structure of the page, sizes of objects, amount of time spent parsing and executing, and at what relative offset from their initiators other objects in the page were needed. The simulator then works by superimposing the desired environment and modulating the amount of time objects spend in each queue. As objects are discovered, downloaded, and executed, they move between the queues. This is the high-level operation. The paper provides more details about incorporating TCP semantics, link sharing, caching, CPU simulation, DOM semantics, and push preload policies. In this example, we would first simulate the fetch of the HTML page, counting the round trip to the server and time to download based on the configured network bandwidth. After the HTML is received, we simulate the discovery of the CSS and JavaScript, which we then put into the downloading queue. Once their download is complete, we add the two images that the JavaScript will download into the delayed queue based on the simulated CPU speed, and start downloading the next image referenced by the HTML. Based on the page profile, we'll simulate the execution delay and start downloading the last two images. And at this point, we've run through the process of loading the page and can construct the final page load time. Simulating page loads work pretty well, speeding up the time it takes to evaluate a push policy by over 3 orders of magnitude, while maintaining a low median error rate of 0.4%. Now, the New York Times page that would have taken 10 days to train takes just 20 minutes. To this point, I've only talked about training with Alohamora. However, the key goal here is to generate these policies at load time in order to adapt to specific conditions. And importantly, we want our solution to work with existing browsers and APIs. Starting with the original web server for a site, we add a co-located module, which houses Alohamora's learned policy generator. To query this model, we need to know the page's dependency graph, as well as inputs that summarize the environment. To collect the dependency graphs, we add a transparent hook to content management systems that track changes to page content and regenerates dependency graphs as needed. These graphs are then used for asynchronous training and cached inside Alohamora. Then, when the client requests a page, they attach information summarizing their environment using existing profiling APIs the browsers already expose. This information is fed into Alohamora's model, along with the corresponding dependency graph. And once a policy is generated, Alohomora collects the necessary objects from the web server using HTTP and ships back the responses to the client based on the policy. We evaluated Alohomora across 500 pages, several devices and networks, cache settings, and more. I'll provide some quick highlights of the results, but the paper contains much more detail. Compared to a baseline of no push preload, Alohomora speeds up page load time by 24 to 61%, and speed index by 19 to 48%. We also compared to the state-of-the-art, Vroom, which enacts static push preload all policies using a client-side request scheduler. Alohamora's policies are 1.4 to 3.6 times faster than Vroom's. And these improvements aren't just theoretical. We deployed Alohomora as a man-in-the-middle proxy on real websites and evaluated policies using mobile devices over real networks. And the performance improvement is largely consistent. Most importantly, because it adapts to changing environments, Alohamora's policies never degrade page load performance, compared to Vroom, which can degrade load times for up to a third of page loads. The paper contains a more detailed evaluation. With that, I'll conclude. The code for Alohomora is open source, and I encourage you to check it out as well as read the paper for more details. Thank you.